Okay, good morning, everybody. Welcome back to Math 115. So today is day 6. I think I forgot to put the welcome screen up on the last video. But today we're going to be talking about section A.4. So before we start, let me run through some announcements. So first of all, you have a homework assignment, A.3, that's due today. A.4, I haven't adjusted the due date yet, but it's going to be due on Wednesday. So whatever we cover today, you'll need to do that homework between now and the end of the day on Wednesday. So just for future reference, all of the homework assignments, whenever they're due on a given day, it's always at the last minute of that day, okay? So it's if A.3 is due on August 29th, which it is, that's today, it's not due until the minute before midnight. That's just so that people don't get confused about whether it's at the end of the day or the beginning of the day. All right, so your next assessment is going to be quiz 1, which is going to be tomorrow. So the sections that are going to be relevant to study for the quiz are going to be sections A.1, A.2, and A.3. And the problems for the quiz are going to come directly from the homework assignments for A.1, A.2, and A.3. So if you want to study, I would suggest maybe looking back at those problems. You don't necessarily have to do them all, but you could look and say, would I know how to do that if that came up on the quiz? Yes or no? And just run through the problems. Most of them probably yes, but if there's a couple that give you trouble, maybe you want to study those. So for the quiz tomorrow, usually what I will do is I will print out quizzes for you all. But the math building is still not ready, which means that I don't have access to a copy machine, so I can't make copies of quizzes. So what I'm going to do instead is I'd like everyone to just bring a piece of paper. Okay, if you have a notebook, just tear out a piece of paper, whatever. I'm going to display the problems up on the screen, okay, and you're going to write down the problem and your solution to the problem on your piece of paper. Does that sound good? Okay, so that's how I used to do it way back before I learned how to use copy machines. So yeah, please bring paper and pencil. I'll bring a little extra paper just in case anybody needs it. 2 other announcements. First of all, vis-a-vis COVID, I've had several people email me saying, oh, I had an exposure to COVID. What do I need to do? Just please stay away. Just stay away from the classroom if you've had an exposure to anyone with COVID. You can literally watch the lectures on YouTube. You can complete the homework remotely. And my office hours right now, at least for the next week, are still going to be remote. So you can literally participate completely remote. Just, I do not mess with that. So if you have an exposure to COVID or if you tested positive for COVID, then definitely please stay home. So if you're exposed, protocol would be go get a test. Once the test is negative, okay, come back. Assuming that you don't have symptoms. All right, so that's COVID. Also, office hours. LeConte, the math building, is still not open yet. They tell us that it will be open next week. I'm somewhat skeptical of that. So for now, office hours will still be remote. So the way that you can get onto office hours is by downloading the app Microsoft Teams. You have already been added into Microsoft Teams. You can log into Microsoft Teams using your email, your USC email, and your USC password. Then you just click on the meeting, you join the meeting, you'll see something like this, and you'll hear my voice, and I'll be able to hear you, and you'll say, I want help with problem 6 on the homework. And then I'll write down the problem, and we'll do it together. So that's office hours. And let me just remind you when those are. They're today, Monday, and Wednesday from 10 a.m. to 11:30 a.m. So if you want help studying for the quiz, I'll be in that meeting after class today as soon as I can get home. And yeah, just come chat. Any administrative questions before we start in on content for today? Okay, doesn't sound like there's any administrative questions, so we're going to move on to content. So let me remind us what we were talking about last time. Hey, what's your name?
Lawson.
Sorry?
Lawson.
Lawson. Okay, let me just put you in that for the attendance. Lawson. There we are. All right. Let me remind us what we were talking about last time. So last time we were talking about rational expressions, and specifically we were talking about how to multiply, divide, and add and subtract rational expressions. So for multiplication and division, it was fairly simple. For multiplication, all we have to do is factor everything and then cross-cancel anything that can be cross-canceled, okay? And then multiply the numerator times numerator, denominator times denominator. What was the big difference between division and multiplication? Yeah, for division, there's just one extra step, right? Which is that you take the second rational expression and you flip it, right? Multiplication by the reciprocal is the same as doing division. So a division problem is really just a multiplication problem with one extra step. Yeah.
For the example, why do you not multiply like x plus 1 times x minus 1?
Why do we not multiply x plus 1 times x minus 1?
Yeah, to like get the same denominator.
Aha, so okay, the question is, why when I'm doing a multiplication problem, do I not need to get a common denominator? Can anybody answer that question for us? That's a great question. Yeah, Griffin?
Multiplying the denominators by each other?
Yeah, so when we're doing a multiplication problem, okay, the rules of multiplication for fractions, say if I do a over b times c over d, what I need to do is actually, I just need to multiply the numerator times the numerator and the denominator times the denominator. So I kind of automatically get the denominator I need by just, well, first of all, I canceled all of this stuff. So I get it by just taking, well, what's left in the denominator here is 1, and what's left in the denominator over here is x minus 1. So I multiply those two together to get x minus 1 in the denominator. What I need to do is, if I add something like 1/3 plus 1/9, the reason I need to get a common denominator is because if I just try to combine these two, what should the denominator be? We don't have a rule for that, right? We have a rule for how to get the new denominator in the multiplication case. But in the addition case, we got to find the common denominator before we can go ahead and just add the numerators, right? Okay. So in that sense, I think that doing the multiplication's easier, right? Because we don't have to find the common denominator. All right, so when do we have to find the common denominator? We have to find the common denominator when we are doing addition and subtraction, right? Okay, so what do? There was a point where I wrote down the steps, I feel like, but maybe not. Okay, so what do? What I like to do is start by factoring, okay? And then what you need to find is what's called the LCM of the two denominators, which means that I need to take each fraction and multiply the top and the bottom of that fraction by the missing factors. What I mean by missing factors are any factors which are present in the opposite expression, which are not present in my expression. So for example, when I had x plus 6, x minus 6, I did not have either of the two factors which were in the other denominator, so I had to multiply both of them on the top and the bottom. Okay, so that was adding and subtracting. And the last loose end that I have to tie up that I guess I just didn't quite make it to was complex fractions. Okay, so there's a couple like this on your homework. If you were confused by that, I apologize. I meant to get to this by the end of class last time. But the way we deal with something like this, where we have like, I don't know, I guess we have, if you count them all, like 4 fractions here, right? 2 in the numerator, 1 in the denominator, and then the whole thing is also a fraction, right? So what I should do anytime I have like fractions within a fraction is I like to work in some sense from the inside to the outside. Okay, which means that I start by focusing on simplifying just the numerator and just the denominator and then I work on simplifying the entire thing. So here's what I could do. I could simplify this top first. Okay, so the way I would do that is by finding a common denominator between 1/2 and 1 over x. What is it? So what's the common denominator between, yeah, 2x, right? So the first expression, I have to multiply by x on the bottom, so I multiply by x on the top as well. I get x over 2x, and then I have a plus, and then I have a 2 over 2x, right? And now the denominator stays the same, x squared minus 4 over 2x, right? So now I can combine the top into x plus 2 divided by 2x, all divided by x squared minus 4 over 2x, right? So now I've got it down to the previous case. I just need to apply division here, which division is the same as what? Very good. It's the same as multiplication by the reciprocal. Okay, so x plus 2 over 2x times 2x over x squared minus 4. Okay, now what should I do? Factor x squared minus 4. Very good. X plus 2, and then we've got 2x, and then x plus 2 and x minus 2. Okay, now I'm nearly there. What do I still need to do? Cancel. I can cancel what? 2x with 2x and x plus 2 with x plus 2. So my final answer will be 1 on the top and x minus 2 on the bottom. Any questions about that example? Yeah. Like right here? Yeah, if I'm ever not writing big enough, by the way, let me know. Okay, so no questions on this one? All right, then let's move on to A.4. Okay, so what is A.4 going to be all about? We're going to talk about radicals and rational exponents. Okay, so radicals, as you know, in math has a little bit of a different meaning than it does in common parlance. So let's talk about what a radical is, and then the simplest kind of one that there is, of course, the square root. Okay, so let's talk about what's called the principal square root. So you probably heard of square roots before. Has anybody heard them referred to as the principal square root before? Let's have a show of hands. Have you ever heard of the principal square root as opposed to just the square root? Okay, a couple people. So the only difference when we talk about the principal square root, okay, is we're talking about a function, which of course we haven't defined what a function is, but we will do that soon. But one of the things that we need to be true about a function is that it should pass what's called the vertical line test. And if you graph the function, well, if you graph the relation y is equal to the square root of x, you actually get a parabola looking like this, which clearly fails the vertical line test because if I put a vertical line through it, it touches at 2 points. So if we want this relation to be turned into a function, what we're going to do is essentially delete the negative part. So when I talk about the principal square root, I'm only talking about the positive one, because of course there's also a negative square root for any real number. Okay, so let's get into that. So the first thing we say is let x be an element of this set. So this is some new notation. So if I draw the capital R with the extra line, of course that refers to the real numbers. Okay, if I draw the plus sign, then that means I'm only referring to the positive ones. Okay, so this is like a bucket, and in my bucket I throw in all of the positive real numbers, but I don't put in any negative ones. How about 0? Do I put in 0? Is 0 a positive real number? Zero is not a positive real number. Why? Can anyone tell me why? Is it because it's not a real number? No, it's not. It is a real number. It's because it's not positive, right? What does positive mean? Positive means larger than 0. So since 0 is not larger than itself, it's not positive. Okay, so anyways, if x is a positive real number, then what is true? X has 2 square roots. Okay, so we have the positive one and the negative one. So if we take the positive one and we square it, we get the same thing as if we take the negative one and square it. So the reason is if you take a negative number times a negative number, the negatives cancel each other out and it becomes positive, right? So we have 2 square roots. But the principal one is the positive one, okay? So we only take positive numbers when we are talking about the principal square root. Okay, so for example, the square root of 4 is plus or minus 2, but the principal square root of 4 is 2. Okay. So let's talk about properties of the principal square root. Or really, yeah, okay, yeah. These are properties of the principal square root. So what does this first one say? Well, the first one says if I take a number and then I square it and then I take its square root, then that is going to give me this weird thing, the absolute value of x. So let's see why that's true. Well, if I took negative, why don't we start with taking 4? If I take 4 and I square it and then I take the square root, then I get the square root of 16, which is of course 4, right? So that works because absolute value of 4 is 4. But what about the negative one? If I were to do the square root of negative 4 squared, well, since I do negative 4 times negative 4, I get the square root of 16, which again gives me 4 if we're doing the principal square root. Okay, so that's an interesting thing. If we take a negative number, then square it, then take the square root, we get back the positive version of that number, aka the absolute value of that number. So that's property number 1. And property number 2 is if I take the square root first and then square it. So the first thing was to say if I square it and then take the square root. Now what we're going to do is we're going to take the square root and then we're going to square it. Well, if we're going to take a square root, the number definitely has to be larger than 0. Because there's no way to multiply 2 numbers which are the same number together and get a negative number unless we're talking about complex numbers. So as long as x is larger than 0, if we take its square root and then we square it, we recover the original number. Fairly simple stuff. You can do and undo squares with square roots. Okay, the second property is that if we do the square root or the principal square root of 2 numbers being multiplied together, that's the same as if we just do the square roots of each number and then multiply. Okay, so I can exchange the order of multiplication and these square roots. Likewise, with division, we know division is just fancy multiplication. So division, if we do the square root of a fraction, it's the same as the square root of the numerator divided by the square root of the denominator. Okay. Any questions about the properties of square roots or the principal square root so far?
Is that x is greater than 0, or is that x is greater than or equal to?
It's greater than or equal to. So you might be wondering, why am I putting x is greater than or equal to here when I was so adamant that 0 is not a positive real number? Well, the reason is because of the language that follows. It says, if x is a positive real number, then x has 2 square roots, r and minus r. So, side note, I guess, if x equals 0, then x has 1 square root, right? namely r equals 0, right? So that's just a side comment, I guess. So we can still take the square root of 0 because 0 times 0 is 0. All right, good question. Any other questions? Palpable silence. All right. Then let's talk about nth roots. Why not make it more complicated, right? So nth roots are things like sometimes we'll say a cube root or a fourth root or a fifth root, etc. Okay, so higher order is the other word we use sometimes. Higher order roots. So order refers to the level of the root. So square root would be order 2, cube root would be order 3, and so on. Okay, so let's have some rules. Well, pretty simple stuff. The first thing to say is that, well, what is the definition of an nth root? Well, an nth root of a number a is another number b such that if I take that number b to the nth power, I get a, right? So we have this relationship that b to the power n should be equal to a. If that is true, then we call b the nth root of a. Okay, now you're noticing probably I've got a bunch of conditions in here, like I want a to be positive, okay? Well, what we really want is to distinguish here between two classes of roots, even-powered roots and odd-powered roots. Can anybody tell me why there's going to be a big difference between even-powered roots and odd-powered roots? Griffin.
If you're cubing a negative number, the end result will be negative.
Very good. In other words, I can take cube roots or odd-powered roots of negative numbers. So we can never do the square root of a negative number. We can never do, well, not never, but not in this class. We can never in this class do the square root or the fourth root or the sixth root of a negative number. However, we can find the cube root or the fifth root or the seventh root of a negative number. Okay, this is because if you multiply a negative number times itself an odd number of times, you can, of course, achieve a negative number of any value. Okay, so let's explain that. So if a is a negative number, and crucially, n is odd, then we say that b is the nth root of a provided that b to the n is equal to a. Okay, so for example, how would I find the cube root of -1? What I want to find is a number such that I want b such that if I do b times b times b, I get -1. So what should b be? In this case, b should be -1. If I multiply -1 times -1 times -1, then I get -1. Okay, so that's odd-powered roots. Okay, so the next thing to say, I've already kind of said, but if a is less than 0, so a is a negative number, and n is even, okay, n is even, then the nth root of a is not a real number, okay? Meaning it's a complex number. But we're not talking about complex. All you need to know is that we cannot do even-powered roots of negative numbers. Okay. And then, finally, the catch-all statement, if a is actually equal to 0, right? So what did we cover so far? We covered if a is positive and if a is negative. So the last case is, what if a is actually equal to 0? Well, if a is equal to 0, the nth root of a is always 0. Okay, because you can just multiply 0 times itself however many times that you need in order to get a, or in order to get 0. All right, any questions about these definitional qualities of principal nth roots? Okay, so like I said, one crucial thing here to refer to nth roots as the principal nth root is, of course, that the root should be the positive root. So, of course, if we do a fourth root, we're also going to get a positive and a negative number. But if we're talking about the principal fourth root, we're only referring to the positive number, which is a fourth root. So that's a way for us to get a unique single number out of these roots. Any questions on these definitions here? Okay, if no questions on the definitions, we're going to see a couple properties and then do a little practice, okay? So let's look at let's look at properties first. Okay, so most of these will probably be pretty familiar to you if you've seen nth powers and nth roots before, but let's go through them just for completeness, I guess. So if I take the nth root of something, and then I take that to the nth power, right? Then I get back my original quantity. Okay? Provided that you can actually take this nth root, i.e. a should be positive or negative if n is odd, and then a should be, well, okay, actually this isn't even true. Oh, this is true for principal square nth roots. Yeah. This is true for principal nth roots. Yes, okay, yeah, I'm sorry. This is fine. Okay, so we take the nth root of a number. Okay, we should stipulate that a is okay. What we should stipulate is that this root should be able to be taken, i.e. if n is an even number, then a should be positive, right? As long as we can actually do this nth root, then if we do the nth root and then we take the nth power, we recover back a. All right, so second step, well, if I do the nth power and then I take the nth root, then depending on whether n is even or n is odd, I'm going to recover either the absolute value of that original number or the actual number itself. Okay? So the next step is a relieving one. We can do the same thing with nth roots as we can with square roots. Namely, if I multiply something under an nth root, I can just take the nth root of each number that I'm multiplying and multiply those together instead. Okay, so that's going to be important for simplifying these guys. So next up, we've also got the fraction property, right? Square root of a fraction is the fraction of the square roots, or the nth roots. So the next one, or the next two are kind of new. 5 and 6 are kind of new. So what do they say? It says, well, if I have two numbers, m and n, well, if I do the mth power of a, and then I take the nth root, well, what rule number 5 says is I can change the order. Instead of doing that, I can take the nth root of a and then do the mth power. Okay, so you can do them in any order that you want. And number 6 says, well, if I take the mth root of the nth root of a, then the way that we combine these is with multiplication. So this should sort of remind you of when we do something like a to the m to the n, right? Then we multiply those powers, right?
Wait, is that m or n?
Which one? Well, there should be one m and one n. Let me maybe draw it a little bit clearer here. So this is the mth root of the nth root of a, and then this is to say that we get the m times nth root. Okay, so if we did the cube root of the square root, that would be equal to the sixth root of a. Cube root of the square root would be the sixth root of a. Any questions on these properties? Okay, then let's do some practice here. So I'm going to do a simple one here to show you how we do this. And then we're going to do a little bit of work with a partner, okay? So the first thing that we want to do when we're simplifying nth roots, okay, is express the radicand. So what I mean by the radicand is whatever is under the square root, okay? So the radicand is what we call whatever is under the square root. So I want to express whatever is under the square root as a product of powers. A product of powers that match the root and use properties 3 and 2. Okay, so what were properties 3 and 2? They're the properties where we can say that the square root of a product is the same as the product of the square roots. So in other words, if I can break down the radicand as two things, one of which I can take the square root of easily, then I can simplify by taking it out. So let's see how that works. I thought I deleted this already. Okay, so let's see how that works. Well, if I wanted to do the cube root of 4 to the 5th power, what I want to do is rewrite 4 to the 5th. In fact, why don't we make it even harder? We'll do 4 to the 15th power. No. I'm going to change that a little bit. We're going to do 4 to the 16th power. Okay, so what can I do here? What I can do is I can take out however many times I can evenly divide 3 into 16. So for example, I could rewrite this as the cube root of 4 to the 15 times 4. Hopefully you agree with me there. So why is this helpful? Well, this is helpful because I can easily take the cube root of 4 to the 15, and then the cube root of 4 is just going to be a little bit of leftover. So let's rewrite a little bit further. Why is it helpful to write 4 to the 15? Well, because 15 is a multiple of 3. I can rewrite this further if I wanted to as 4 cubed times 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 4, right? And now what is true? I can rewrite that as the cube root of 4 cubed times the cube root of 4 cubed, times the cube root of 4 cubed, times 4, times the cube root of 4. Using the rule, which says that the cube root of a product is the same as the product of the cube roots. And we had another rule, which says that if I do the cube root of something getting cubed, I just recover that original thing. So what do I get? I get 4 times 4 times 4 times 4 times 4 times the cube root of 4. In other words, I get 4 to the 5th times the cube root of 4. Okay, so a lot of the time, okay, I'm not going to write out all of this business. What I'm going to recognize is that 15 is a multiple of 3. So what is going to come out of the radical here is 4 with power 15 divided by 3. Okay, so I'm going to take 4 to the 5th out because I divide 15 by whatever the root is, which is, in this case, 3. So this 4, unfortunately, has to stay inside because there's no nice way for me to express the cube root of 4 without using, like, decimals. So this is the game that we're going to play whenever we're simplifying radicals. All right, any questions on this one, on this example that we just did? Okay, then let's work with a partner to try to simplify these two expressions. Okay, so 5 to the 5th times 16, we're taking the square root. So you'll notice, by the way, if I don't put a number here, I'm always talking about the square root. If I do put a number, then it'll be whatever that root is. All right, so let's try to simplify these with a partner using the methodology just described. And I'll walk around and help if you have questions.
Can you scroll up a little bit?
Scroll up a little bit.
To the last one. At the bottom of it.
Sorry, like this. Second.
Is that 162?
That is 162.
Maybe you do you pull up two goes in the corner. Well, this is an imaginary two.
Oh, yeah, it's your imaginary too.
Well, no. He did 5 to the 15th. Times 4. So when he's
You pull up 4 fives. No, I think you pull 2 fives.
Yeah.
Yeah, so then it's 50. Wait, I mean, sorry, 100.
And then divide the 16 by 2. How's that?
Times 10.
Yeah, because it's what, it's 4. So what if you change 16?
In the second one, right? Or no, the first one. Right. So 5 to the 5th. I like how you put it here, right? So it is 5 to the 4th, right? 4 because 4 is divisible by 2, right? So now this can come outside, right? So this is 5 to the 4th, which is the same as
It's 2 fives.
5 to the 4th, you agree, is the same as this, we can do, right, as the square root of 5 squared.
Or like 5 squared times 8.
Yes. Times 5 times 16. And I can rewrite that as the square root of 5 squared times the square root of 5 times 16. Yes. Now, how do I deal with something like this? If I take the square root of something squared, I get back that original thing. So what am I going to have? 5 squared, right? Because I took that and squared it, right? So in other words, the way that the root works is if we have a power here which is divisible by that root, then it comes out as 5 to the power, which is going to be what the power was 4. In other words, 4. Divided by the power of the root. So I definitely 4 divided by 2, we get 2. And we still have our 5 times 16 left over.
I think you have to.
Probably just take out 1 2. Well, I want to my version.
You're supposed to take the 4 out, right? And then whenever
You can take them out in any order that you want, right? The crucial thing here is that, look, we can start, right, by rewriting this. I mean, we have 3 things being multiplied, right? That's the same as the square root of 5 to the 4 times the square root of 5 times the square root of 16. Agree? Would you agree with me that 3 times 2 times 4 is the same as 4 times 3 times 2? Right? We can do multiplication in any order, right? So this becomes 25 times the square root of 5 times 4, right? So the 4 should be multiplied with 25 to get us. Yeah, I mean, if you want, or you can. But the point is, right, that, okay, yes, 5 squared root 20. Wait.
I didn't take the 4 out.
I was gonna say, what you should have here, I think, is 5 times 4 squared, right? Which would be 5 times 16. Still left inside, right? So you get 5 squared, and then you have a square root, and then you have 5 times squared, right? And then you can rewrite this. how? Yep, which is 4, right?
Okay, so I think maybe here.
And then you can multiply those first two, right? Multiplication then.
So how would you do this one though?
It is very different. We'll talk about that in a minute.
Is this like simplified as we get together?
So you rewrite it as 5 to the 4, but the 5 to the 4 I think should still be square root here. I could rewrite the square root of 5 as the square root. So what I'm going to end up with is square root of 5 to the 4 times square root of 5 times square root of 16.
I'm still
But when you put in here, you understand the square root of 5 to the 4, right? So the way that you think about that is you agree with 5 to the 4 is 5 here. If I take the square root of something squared, I get back that original thing, right? So if I do the square root of 5 squared, I get 5 squared. So that's how it's done. So I can say right here, the square root, and before the square root, I'm going to 5.
So it would not be a real.
You know, and left hand side, it's just down 5. Well, okay, yeah. So I got first 16, right? And then
For number 3, it would not be a real number.
It's confusing at first, but then it's that makes sense. Because I was confused. I learned the research calculus.
Okay, I'd like to come back together as a group. I know there's lots of questions. I'll try generally when I'm walking around to hit different people each time. But if you have a question that you didn't get answered, then please either stay after class or come to office hours and we can talk about it, okay? But hopefully I can answer some of these questions right now by going through these problems. So first, maybe let me add a page here because I did not leave myself enough space to do these problems. Okay, so let's try these. So, how much time do I got? Ooh, I'm low on time. All right, so I want to handle something like the square root of 5 to the 5th power times 16. So using our previous methodology, then what I should do is I should rewrite this root using the maximal power such that that power is divisible by 2 in this case, so 2. So I'm going to rewrite this as the square root of 5 to the 4 times 5 times 16. Now I'm going to rewrite that as the square root of 5 to the 4 times the square root of 5 times the square root of 16. And I'll rewrite 5 to the 4 one more time as 5 squared squared. Okay, if I do the square root of something squared, what do I get back? I get back the original quantity, right? Because square roots and squares undo one another. So, in other words, this square root and this square here undo one another, and I'm left with just what is left inside, which is 5 squared. Now, I multiply that with the square root of 5, and I multiply that with the square root of 16, which everyone, I think, should be comfortable with doing, is 4. Okay, so we get 4. So now, of course, I can do multiplication in any order that I want, right? So I can do 5 squared times 4 first, and then multiply that with the square root of 5. So I'm going to bring the 4 over. I'm going to rewrite this as either 5 squared times 4 times the square root of 5, or if you want, 100 times the square root of 5. Okay, let's start with this one, because I saw a lot of questions on this one out in the group. Does anybody still have questions after seeing the solution go out here? Okay, so you'll notice in the end, basically what I'm doing here is I'm removing from the inside of this radical the maximal number of powers which is divisible by 2, which in this case is 4, and it comes out as 5 squared because we divide 4 by 2 to get 2. So questions on that? Okay, if you have more questions on that, please stay after or come to office hours. So the next one is harder, right? 162 times a to the 4th power. Okay, so let's start by handling it if a is positive. So if a is positive, that's the simplest situation. Then what is going to happen? Well, we can rewrite 162 as, I think we can rewrite it as 81 times 2, right? Times a to the 4th. And we can rewrite this as the 4th root of 3 to the 4, because 9 times 9 is 81, and 3 times 3 is 9. So 3 times 3 times 3 times 3 would be 9 times 9 would be 81. Multiply by 2, multiply by a to the 4th. And this time I'm not going to write it all out. I'm just going to pull things out. So the 3 to the 4th, if I do the 4th root, we divide 4 by 4 and get just 1. So we're left with 3. And also the a to the 4th can come out as a. And then left inside, I have the 4th root of 2. Okay, what would change about this if a was a negative number? Yeah, Connor?
It wouldn't exist because you can't take like an even root of a negative.
We can't take the even root of a negative number. That's true. However, if I take a negative number and I take it to the 4th power, is it still going to be negative? It's going to be positive. So I'm going to take that negative number, take it to the 4th power, now it's positive. Then I do the 4th root of the positive version. And what am I going to get here instead of the original number a? I'm going to get the absolute value of a. Okay, so if a is less than 0, we're going to get 3 times the absolute value of a times the 4th root of 2. So why is that true? That's true because of rule number 2 here, right? The nth root of a to the n. If n is even, we get the absolute value of a. Okay, so that's the only thing that will change there. All right, that's it for today. I'll see you all tomorrow for the quiz. And then next time we'll talk more.
Have a good day.
Yep, you too.